So welcome everybody. My name is Utkarsh Krishna. I'm the Vice Chair for the IEEE Microwave Theory and Technical Society Santa Clara Valley Chapter, or MTT-SCV. Welcome to the technical presentation for the month of August 2020. The title of which is, What is my measurement equipment actually doing? The implications for 5G, millimeter wave, and related applications. Our speaker today is MTTS Distinguished Microwave Lecturer and Engineering Fellow at Anritsu, Dr. Jon Martens. Welcome, John. We are very fortunate to have you. It's a great pleasure and honor. Before we go on to the actual talk, just a few things to note. This meeting is being recorded, and also it's being broadcast live on both Zoom as well as Facebook Live. Links to the video and the slides will be made available to all registrants. Please keep your cameras off and microphones muted to help with bandwidth issues and background noise. Please post your questions in the chat window to everyone. One of our officers will monitor the chat window, and we'll be taking breaks every 20 minutes or so to answer them. Please ensure that your display name in Zoom, if that's the platform you're using, matches the one you used to register. This will make it easy for us to check you in and keep records. If you did not register and were forwarded this link, please send Utkarsh Krishna, that's myself, a private chat message in Zoom with your name and email address so that I can register and check you in. Please support us by becoming a member. Join IEEE and MTTS if you haven't already. It's only with your support that we can continue to bring you these talks. So if you haven't joined yet, please consider joining. Also, please follow us on LinkedIn using the hashtag MTT-SCV. That way you can get access to any announcements we make from our channel at the moment we make it, keep track of any future events, and so on. The agenda for today, or the rest of the slide set, we'll be looking at some COVID-19 updates, followed by the officers for the two societies. I forgot to mention, this talk is actually a joint talk. It's co-sponsored by the IEEE Circuits and Systems Society, as well as MTTS. So we'll be looking at who are the officers for these two chapters. After which we will go on to an introduction to our speaker and today's talk. As far as COVID-19 updates, all our in-person meetings organized by our chapter are canceled, and we're holding only online or webinar format meetings, such as this one. To introduce the two chapters, I would now like to call upon our Chairman, Mr. Jay Banwait. So Jay.
Thank you, Akash. Actually, my power just went out on my computer and was able to get back in about a couple of seconds before you introduced me. Anyway, as Utkarsh said, this is a joint presentation by the Circuit and System Society, as well as the MTTS, Microwave Theory and Transactions. As Utkarsh mentioned, I'm the chair, Jay Banwait. Vice chair is Utkarsh Krishna. Secretary is Tan Tui, and treasurer is Tom McKay. Next slide. Our sister chapter, Circuits and System Society, chair is Imran Bashir, the vice chair Amit Jha, and the secretary is George Chen. Next. So as Utkarsh mentioned, we are honored to have Dr. Jon Martens as the presenter for this presentation today. Jon Martens has been with Anritsu since 1995, where he is currently an engineering fellow. He's also a distinguished microwave lecturer of the MTTS class of 2020-2022. His research interests include measurement system architecture and pathologies, millimeter wave circuit and system design, and a wide range of microwave measurement processes to include material analysis, nonlinear and quasi-linear characterization, optical interaction, and calibration. He is also the inventor or co-inventor on over 17 patents and has co-authored several book chapters and over 50 technical publications. Dr. Martin is past chair of the MTT Measurement Technical Subcommittee and is a past president of the Measurement Society, RFTAG, and is still active in both. He's a member of the Technical Program Subcommittee for the International Microwave Symposium and RFTAG, and is a former associate editor for the Transactional on Microwave Theory and Transactions, Microwave Theory and Techniques. So, next. Today's presentation, as was mentioned, is titled "What is my measurement equipment actually doing? Implication for 5G, millimeter wave, and related applications." The abstract is, I'm sure you folks have already read it, but let me just quickly go through it. It's the abstract is current microwave and high frequency instrumentation for many tasks behind the scenes, even more so in the millimeter wave and high modulation rate regimes, pertinent to near and upcoming communication standards and other applications. And it's easy to lose track of how the equipment, the processing algorithms, the setup, and the signals are interacting. By exploring the measurement mechanics within some common instruments under practical conditions, it may be easier to understand where sensitivities or anomalies might increase and how to mitigate them. Through a study of example architecture and measurements, including those in the 100 gigahertz range and those with wide modulation bandwidths where linearity, dynamic range, and other physical metrics are stressed, even more mechanisms and ideas for better measurements will be explored. So with next slide. So without further ado, I think that's our last slide. Let me present Dr. Jon Martens. John, if you want to share your screen.
It says host disabled participant screen sharing.
Gosh, are you? Go ahead.
Hold on, let me fix that. I don't know how that happened. Sorry about that.
Thank you for the very nice introduction, and thank you for the invitation to speak today. Looking forward to it.
We're honored to have you, John. Thank you.
Okay, guys, give me just 1 second here. I'll need to figure out. Can you share? Can you try again, John?
Nope.
Oh, no, because I'm looking at the options and it says everybody should be able to share. It's interesting.
With Gosh, do you have the slide set?
I don't, but if you can send that to me, John, maybe that's because it says here it should be, you should be able to share it, and we've never had this problem before, so not sure.
Let's just have a backup plan just in case it doesn't work out.
So Jay, can you try sharing? Do you have the same problem? I'm just curious.
Hoping that's visible.
Yep.
All right. Again, thank you for the invitation to speak today, and thank MTT for sponsoring the DML program. And as many talks in the last several years, we have to have this obligatory little chart of spectrum as 5G and 6G communication standards are certainly very important in development today. But in particular, there are some aspects of it I want to focus on. The obvious ones, of course, are wider instantaneous bandwidths to 400 megahertz in FR2 for 5G currently, and wider ones promised for future editions. And modest millimeter wave frequencies, at least for now, up to 52 gigahertz in the 3GPP standard, and certain 6G proposals are well into the terahertz range, at least from a regulatory point of view. Let's wait to see it when and if those get implemented. Some relatively stringent adjacent channel power requirements in part of some of the 5G specifications, and stringent from a measurement point of view as much as anything. And then not so much part of the standards, but just a practicality as integration levels increase, is the larger number of over-the-air test requirements and how that impacts particularly things like measurement repeatability and calibrations. If we broaden the scope to other millimeter wave applications, such as local distribution, there's a certain amount of work going on, and well above 200 gigahertz even in some of these nicer lower loss atmospheric windows, or relatively lower loss. Some interesting aspects, at least in some of this work, is relatively high power levels, at least compared to what has been done in those frequency ranges. And as at lower frequency ranges, the consideration of linearity and the presence of wideband interferers is important. Millimeter wave imaging and radar has been in a lot of research areas and some commercial areas recently for the obvious benefits of resolution. And that presents some sometimes severe noise requirements, both for the devices being made and the measurement equipment to look at them. And underlying all of these applications is just device development, where wideband models are needed, not just to cover the specific application frequency ranges, but perhaps harmonics for nonlinear analysis, perhaps mixing products of some modulation energy. And in other words, more than just a narrow swath of frequency has to be covered in the model development, and with a lot of different measurements of interest. So if one sort of collapses all these things down onto the measurement implications, there are, well, some obvious things, the frequencies, of course. And we talked about the measurement media and the characterization. And one that isn't talked about as much sometimes is the needed uncertainties in those measurements, although much more so currently than a few years ago. And that's the obvious case that if you require too tight an uncertainty in the measurement, you'll spend too much energy on test protocols and equipment. And if it's too loose a required uncertainty, your end device may not fulfill your needs. So the talk we're going to break down into some classical sort of equipment types that most of you are probably very familiar with. And the little subplot in this whole talk, which I'll reveal now, is there's less of a distinction between these categories than there once was, and the trend is probably continuing in that direction. But we'll start off with network analysis as one of them. And you may be very familiar with this kind of block diagram, where there's one or more stimulus sources, usually just a sinusoid, maybe switched, there may just be lots of sources. Some signal separation devices to pull off an incident and reflected and transmitted signals. Some down converters to generate these A and B waves that can be digitized. And then some calibration is applied to take out loss in cables, mismatch in the VNA itself, and other variables. So just gonna spend a few minutes looking at how some of these piece parts are trending as we go to higher frequency measurements. And one of those is the directional devices, which may be a directional coupler, doesn't have to be, can be a resistive splitter in some cases. And this hasn't tended to be a limiting factor too much as we move to millimeter wave measurements. The technology's kept up pretty well. And just an example here is a broadband coupler intended to cover about 30 to 220 gigahertz. And the coupling factor is higher than the undesired isolation or the uncoupled direction over all that range, which is sort of what you'd like to have most of the time. But that again hasn't been that much of a limiting factor in terms of how it reacts with stability, and certainly not direct uncertainties. The sources themselves are a little more interesting in that historically in the network analysis universe, signal purity was not the highest priority. And for small signal-less parameters, that makes a certain amount of sense in that you know what frequency you're measuring at. And you're not likely to put the DUT into some unknown operating state. But that's been changing as a wider variety of measurements are being demanded of the instrumentation, like harmonics and intermodulation distortion. But also if you're driving this device in a quasi-linear way, then too much harmonic energy can alter its bias point and cause other issues. What that means from a millimeter wave point of view is controlling harmonics and subharmonics in particular gets to be a bit more of a challenge since switched filters get very lossy and present some problems. So there's a lot of work going on in that area to control those. Another aspect of the transmit side, I guess, so to speak, is power control. And that may be for something as simple as a swept power gain compression kind of measurement, which is sort of shown in a little graph in the lower right. But it may just be you want some reasonable control of power at a pretty low level, as fine dimension transistors may compress at -40, -50 dBm or sometimes less. So just having accurate control there is important. And how one has to do that sort of changes a bit with frequency as well. If one looks at this little diagram, which is really just a leveling loop with a lot of different added things in it. If you focus on the far right, there may be some kind of coupled detector, some amplification, maybe logging, difference nodes, some integration, and then it feeds into some variable attenuator, variable gain amp, whatever, to complete a negative feedback loop. And that works fine in principle at all frequencies. The trouble if one tries to do this directly, say in the hundreds of gigahertz, is with a single detection scheme like this, is the amount of noise energy you're integrating over that bandwidth can just swamp your available detection range. So that can be a challenge to get good power control, as well as the sensitivity of the detectors over that kind of range can be varying and perhaps limited. So some techniques that are used are essentially to move the detection to other places. One could put it before a final multiplier, which certainly makes it easier from a noise point of view, but now you have to account for any drift in this multiplier over time, as well as its slope, of course. And another approach, which one is seeing more at millimeter wave frequencies, is a heterodyne detection kind of a scheme that allows you to control the noise energy in a tighter bandwidth and get better power control. If one moves over to the receiver, one challenge here, of course, is getting a decent noise figure, since you have this coupling loss right in the front. So it doesn't make things easy from a classical receiver design point of view. There may be an LNA. It does have to be broadband for these applications, very good linearity, that's fine. There may be some switched attenuation or maybe even switched gain, depending on the system. A couple of challenges there in that because this is towards the front end, any changes in these gain states will tend to affect input match as well as, of course, transmission. So you may need a new calibration for every state. So that can be a bit painful. And of course, at higher and higher frequencies, the through insertion loss of any kind of switch structure like that can get to be significant. So that tends to be a bit less common above, say, the 100 gigahertz kind of realm. Focusing next on just the down converter itself, certainly at lower frequencies, just a fundamental mixer is of course common as in any other transceiver design. But at the higher millimeter wave frequencies, that's a bit of a challenge. Creating a fundamental LO with good noise performance over 100 gigahertz is a bit of a challenge, and even if you're using some multipliers, getting all of that filtering exactly right takes cost, takes power. And finally, in a multi-channel receiver, such as a network analyzer where an LO might be shared, the isolation between paths can be a bit of a challenge. So as in an awful lot of other millimeter wave transceivers, a subharmonic kind of scheme is not uncommon. And it could be a direct subharmonic conversion, this factor J, or there could be some incomplete filtering with an external multiplier, this factor K, doesn't really matter here. The impact of that, of course, is a number of receiver windows will exist where noise energy present at the port will convert to the IF at some of these other, I guess, harmonically related positions. So that'll degrade noise performance a bit more, as well as open one up for some spurious responses. And another impact of that, of course, is on the linearity of that converter, and that ends up being pretty important for some of the quasi-linear measurements we talked about earlier. And a couple of example plots here of two different systems, one about 110 gigahertz broadband instrument, and another in the 330 to 500 gigahertz range. And these are third order intercept products, so a good, or at least a classical linearity metric. And while a comparison between these isn't entirely fair because the technologies are different, you can see numerically there is a drop of the intercept product with frequency. And that shouldn't be too surprising, at least intuitively, since the breakdown voltages are going to drop in the converter elements just from feature size. And that tends to be a fairly dominant linearity factor in these converters. From a practical point of view, it isn't that dire a situation, since typically there are lower drive amplitudes at the higher frequencies as well. So the net uncertainty impact may be a bit of a wash. So how do these get implemented in practice? And one may already be using these kind of structures where you have millimeter wave modules attached to some microwave VNA. So a common approach for certain just practical logistical reasons, but it also valuably gets the test port out very close to the DUT or to the wafer probe or the final structure. So you don't have a crazy amount of loss between the instrument port and the device, which of course impacts dynamic range, it impacts stability and other things. Since even 100 gigahertz, 3-4 dB for 10 centimeters of cabling is not unusual, if not higher than that. And even waveguide losses in the couple hundred gigahertz range aren't insignificant. We talked a lot about the LO structure before, and that's going to be another recurring theme as we go along here, in that you have these fairly substantial multipliers in some cases, and particularly when you get to the terahertz range, these LO multipliers may be on the scale of 30, 40, 50, or something like that. And of course, phase noise tends to multiply with that multiplication factor. And you can indeed see some effects. And the graph on the lower right here is sort of the impact of injecting some LO noise, wideband noise, admittedly. And there's looking at the conversion efficiency of this harmonic converter up front. So we're not looking at noise figure or anything even remotely subtle. We're just looking at conversion efficiency. And you notice when you get to a high enough noise injection level, the conversion just collapses. And I guess one way of thinking about that is more in the time domain, where the converter is a switching element. And that switching transition has been so fuzzed by the noise injection that it really doesn't create two proper states. And so that behooves one then to pay attention to the LO chain, which all the instrument folks have to think about. And if you're creating these down converters yourselves for your own test equipment, that's certainly something that's important. Now, if one wants a broadband kind of scheme, not just say a waveguide band up at 100 or 200 gigahertz, there are broadband systems around. And typically those are constructed with some kind of multiplexing scheme, although switching can be used in some cases. And this is just a sketch of one such approach where both the stimulus multiplication is just multiplexed onto a main line, and then a couple of different receiver systems are multiplexed just by nature of their couplers. And that allows you to have this central conductor that's a DC path. So it allows a low freq, allows biasing, and a few other things. But the advantage of this kind of approach, particularly in an on-wafer kind of situation, is not having to change modules and probes as you try to cover wider frequency ranges. And then there's calibrations, which everyone who's used VNA has been forced to deal with, and sometimes not happy about having to deal with it. And really what's happening here is there are imperfections. Some are sort of obvious, like cable loss to the DUT, but others are behind the scenes, such as mismatch within the VNA, frequency response slope within the VNA, and so on. And the whole premise is that if you have some known standards you can connect out here at these reference planes, you can solve for the behaviors back here and remove them. And this has been a cottage industry for many decades, actually, and you probably recognize this alphabet soup of different algorithms that are available, which, just to make everything more confusing, there isn't a lot of consistency on what the letters and the acronyms stand for, and there are multiple names for the same algorithm. And I won't be able to deconvolve all of this today, but there are a couple of simple points I want to make, particularly vis-a-vis the higher frequency measurements. And open short load is probably the calibration method people are most familiar with, and it has some friends based on offset shorts in a load or just offset shorts. And the premise of these techniques is you tell the instrument exactly what the S parameters are of each standard. And the instrument will do what it has to reproduce those values it's told. So as a sidebar, that makes using one of these standards as a verification device not terribly productive, since the VNA is just going to try to reproduce what it was told. But anyway, the historical method of defining, say, this short was a simple circuit model. For example, an offset inductance for each standard, frequency dependent inductance, admittedly. But that causes some problems in the higher frequencies, since just a simple transmission line plus an inductor doesn't do a real good job of describing a standard that's getting on the scale of a wavelength and size. So a more recent approach has been to provide tabular S parameters versus frequency, which could be from transfer calibration measurements that the manufacturer does. It could be from EM simulations. It could be from a combination of those. And that can make an accuracy difference. And the plot on the lower right is a measurement of a verification device, but you can view the amount of ripple in that chart as a metric of one component of uncertainty. So less ripple is better. And the dashed curve is the old approach where inductance was specified as a polynomial in frequency. And the S1P, as you can guess from the file name extension, is a tabular form. Another popular family of calibrations is the Throughreflect line group, which you've probably heard of as well. And this is a family that's based on ideality of transmission lines, where it's assumed when you have two line lengths, the only difference between those S parameters should be something related to the propagation constant times the length difference. So really what that means is the impedances of those lines are the same, and you can launch to them in the same way. That's where this method can run into a little bit of trouble if you have a low repeatability environment. The launching parasitics aren't consistent. And in that case, the TRL family has some problems, but In more controlled environments, it's probably has the lowest uncertainties of most of the calibration methods. And more recently, there's been a variant on that, which is bringing the calibration slightly more into the statistical realm, where you use a lot of transmission lines, and then you get some immunity from, say, a repeatability error or one line having an odd characteristic impedance or something like that. In that in a least squares sense, the optimal solution from all the data is what's solved for. And so that's particularly in the metrology world on wafer, that is a extremely popular technique. And one little set of examples is shown here in the lower left, is just using a basic 2 transmission line calibration. And a calibration was done 10 times and the same device was measured after each cal. And this is just a scatter in that particular data. So you see a couple of little areas where there's some divergence, which in this case happened to be the touchdown to one of the lines was a little problematic because of some pad damage. This is a non-wafer kind of measurement. But the same approach was done with a 4-line kind of calibration, and the divergence was noticeably less in that case. So this is a moving trend in the higher frequency calibration world. The downside being, of course, you need more standards. Moving to a slightly more practical world where you have a test fixture where you have to connect your device. This can present a bit more of a challenge, since at this DUT plane in the middle, it may not be a terribly high repeatability range if it's a spring points or some kind of pin contact. But still, you want to move the reference planes into that inner plane. And there are a number of ways of doing that, and that's been a significant development in the last few years, is how to characterize these fixtures in a convenient way that's sufficiently accurate for measuring things like, well, fixtures that are up to 110 gigahertz in this little shot here. And one approach that's led to a number of different algorithms is to add some assumptions about the fixture to reduce the stress on the standards at this reference plane. And those assumptions might be symmetry. They can be, where is the mismatch located, for example, is it only at these launch points? And taking advantage of that information can let you reduce some of the stress on both repeatability and on what the standards have to do. Moving to the other media problem we talked about earlier, over the air, where you're trying to calibrate with a free space path as being your transmission line, opens up some other interesting challenges. And one first question is, what's the path loss? And that'll be dependent on how large your spacing is and everything else, of course, antenna gain levels. But if these losses are high enough, a lot of the things you would normally have to correct for, like mismatch interactions, become a lot less important. So you might get lucky and just a normalization kind of calibration is all that's needed. And for example, for a lot of antenna pattern measurements and certain beam configuration measurements, that works just fine. But for smaller ranges, mismatch can come back into play. And as you might expect, just using a normalization can lead to a fair amount of ripple, which is where what this blue curve is in the middle. But if you look a little more carefully at this curve, you'll notice there's a couple of different spatial frequency things going on in it. There's obviously the high frequency ripple in here, but then there's some lower frequency thing going on here. And really what that comes from is a couple of different path length differences causing mismatch variances. And many of the calibration methods at Alphabet Soup we looked at earlier will all work when you do have to think about match. But one method is reasonably popular in that space. That's the Linearity match algorithm. And it's a little counterintuitive at first how these standards are arrived at. But if you think about it, a line, that's sort of easy. You're pointing your 2 antennas at each other. A reflect could be a short, that's just a metal plate normal to the pad. And an important point about this algorithm family is you don't really need to know much about this reflect standard. It's not like short open load where you have to tell it the S parameters. It's really just sort of requires the reflect be symmetric is really the important thing there. So you can be a little bit sloppy with this standard and not take a big uncertainty hit. And the match, while you could put an absorber in here to take care of it, actually, if you're in a chamber and the walls are reasonably absorptive, if you just tilt this plate at a 45-degree angle, you're really getting no reflection into the antenna. And that works reasonably well as a match standard. If we sort of throw all these things together and try to get a bigger picture of overall uncertainties, I mean, here are some of the common mechanisms. Noise floor and trace noise, and although we didn't talk about it too much here, they don't tend to get worse that rapidly as we go higher and higher in frequency. They do a bit, but the technologies are keeping pace, so those aren't degrading too fast. Residual calibration errors, how well do you know your standards is really what that boils down to. And that isn't getting fast very dramatically either. Linearity, we mentioned, it is getting worse in absolute terms, but not so much in net terms, and I'll show a curve in a minute to explore that a little more. What does get worse a little more rapidly are things in the area of repeatability and drift. And a little example here on repeatability, just related to connectors, is shown here in the bottom. And the picture on the left is a reflection measurement using coax. This is a 0.8 millimeter connector, so up to 145 gigahertz. And a device was measured. It was connected and disconnected 1,000 times and then measured again. And the difference in dB terms, vector difference in dB terms, is just plotted here, so somewhere in the 50s. And that's a little bit worse than lower microwave frequencies. Somewhere in the 40 gigahertz range, you might be in the mid 60s, but that's numerically, that's fairly common. But over on the right is a waveguide measurement. Now this is higher frequency, about a factor of 5 higher. Same kind of concept where we just disconnect and reconnect, but this was only 6 times. And you'll notice, and it's the same metric, but you'll notice the numbers creeping up into the 20s. And that's pretty significant. And that's going to swamp all these other uncertainty terms. Now this is with a classic waveguide flange, which was designed many, many years ago with dimensional tolerances that were more appropriate for lower frequencies. So in recent years, there have been new standard flanges developed. P1785 is the name of one such standard to help improve those repeatability numbers. So if one combines these to figure out a net transmission magnitude uncertainty, and this is a really simple model, it's plotted here, but we have the transmission of the device you're trying to measure on the x-axis and uncertainty, of course, on the y for a couple of systems, our 110 gig system and our 500 gig banded system over here. And you'll notice a few things structurally. There's this central asymptote, and things that go into that are calibration terms we talked about, which aren't too significant here, but also repeatability and drift, which tend not to be too level sensitive. And so that's gotten a bit worse. You can see that just from the scale. This lower corner is really determined when the noise floor takes over. And if you look at the level at which noise floor is adding about a ½ dB of uncertainty, okay, that's moved up a bit, maybe from minus 85, minus 90 to somewhere in the minus 75 dB range. So, okay, it moved a little bit. And the upper corner is from compression. And while we showed earlier that the absolute intercept point might have gotten worse, for these two systems, the default power is a lot lower at the higher frequency. So that's sort of where that wash came into play. If we focus a little more on our over-the-air problem, then the repeatability is now a lot more of a mechanical issue. And just as one little example of that, suppose we're measuring an array, and this is an end shot of it as a little green rectangle. And we're just trying to measure, let's say, the phase transfer through each element of this array. But we didn't mount it quite right. So it's tilted relative to the measurement antenna by the little black arrow. And this, suppose we're doing this at 38 gigahertz, so one of the FR2 frequency ranges. If we're off by 1/10 of a millimeter, the added phase error is a few degrees, so you've roughly doubled the total phase uncertainty budget in this measurement, which isn't too terrible. But if you're going to a 1/2 millimeter, now you've had almost 20 degrees of phase uncertainty when you're at the end of the array, which is, of course, the worst case position from that. So that's pretty significant, and you sort of swamped all the other uncertainty terms when you've done that. Another challenge can be multipath. If you think about our cartoon of a chamber in the upper right here, and you're radiating a signal from the device, there's going to be some reflection off this not perfect absorber on the walls, and this mounting jig may have some reflection associated with it. So these multiple paths can all arrive at the receive antenna, but with different delays. So you can get some ripple structure, which is really what's shown in blue. And fortunately, they do have different time delays, so you can foresee there might be some amelioration methods available here. And indeed, there are the classical VNA time domain techniques where you transform the time domain, isolate out the part you care about, throw away the rest, and then transform back to the freak domain. And that's really what's shown here in gray. So you can take care of a fair number of problems, assuming these multipaths are A, sufficiently different in distance, and B, you have enough sweep range, you can get enough resolution out of that, since resolution goes as 1 over the sweep range. So that device is sort of narrow band that presents a bit of a challenge. There are some other approaches where if you have enough modulation bandwidth on these devices, you can actually gate the acquisition and do the same kind of time separation, but physically. Now, I'll dive a little bit more into the measuring in the far field, although this certainly isn't an antenna talk, but there's some interesting handling of measurement data I want to get to here. And the objective is usually to want to be able to measure in the far field, since you can make a plane wave assumption at that place, and analysis of the data gets a lot simpler. But for larger devices and higher frequencies, that distance required gets pretty large, and it may not be practical, may not have a large enough chamber or a large enough setup area to do that. So one approach is a compact range, and these are extremely popular, where a reflector, which is shown by the number 4 here, parabolic or some other curved surface that creates a plane wave area near the DUT, can place you out effectively at this range. The downside is it can only hold that plane wave construct over a finite dimension, so it does put some more constraints on the DUT size. So another approach is to actually measure in the near field, so a much smaller distance, and then apply some transformations to get the equivalent far field result. But that does place some constraints on the underlying data, and that's where I want to spend a minute or two looking at. And there are many ways of doing that kind of transformation, but some of them look basically like a two-dimensional Fourier transform, where this E sub I is some kind of field quantity which we'll take to be linearly related to some S parameters. And we'll transform it spatially to get the far field result. But an interesting question is, okay, I've got some uncertainty in this measurement of my S parameters. How is that going to affect the transform result? And a parallel problem to that is if the instrument time domain I talked about earlier, where you're taking the freak domain data and going into time, the same kind of question rises. What do my uncertainties look like in time domain in that case? And so we can look at this integration, and suppose we just had random or oscillatory errors on this E sub I. And if the scaling is right, they're just going to average out. So the sensitivity you wouldn't expect to be very high at all. On the other hand, if there are some spatially monotonic errors, and this could come from stage mechanical accuracy, or cable flex if it uniformly bends or unbends as we move from one part of the setup to another. One could see the phase changing monotonically with space. This integration is going to tend to accentuate that kind of error, and you'd expect some high sensitivities. And then there are those where they just pass through the integration unaffected. For example, if two polarizations are needed to create this E sub I, and our receivers are not calibrated the same way, those kind of things will pass through directed. And this falls into the whole category of correlated uncertainties. And what's happening here is if the uncertainty in two different positions is correlated, like our cable flex, you can tend to see some expanded effects in the outcome. And that's been a big area of work in the measurement world for a few years now. But let's look at a little numerical example. Here in the upper left, we have some raw near field collected data. This is just amplitude. And in the upper right, we have the transform result. So, okay, that's fine. But now we're going to add some noise, which could be from trace noise. It could be from signal to noise ratio if the path losses are large enough. And it's a lot of noise since this is a linear scale. There's a lot going on here. But if you look at the transform result, not much changed. And the eyeball comparison is reasonably fair in this case since both scales are linear. But now if we add a monotonic error in phase in one axis, which could be the mechanism we talked about before, you see some pretty significant distortions. We've got some broadening in one dimension. The peak amplitude is much lower than we started. And from just looking at the incoming data, if you only looked at magnitude, you wouldn't think anything was wrong at all. But the transformed result was quite a ways off. So to pull all the over-the-air things together in one little example, at least along the lines of what needs to be considered, suppose we have an array like shown here where there's some magnitude and phase adjust and maybe some power amplifier per element. And we want to measure gain, measure phase, measure distortion perhaps, and we want to be efficient about it in a test way. So some of the calibration considerations, what are the path losses? We sort of talked about that. And what are the mismatch levels, say, of this device or of the instrument? So you can work those against each other. That'll help you determine how significant a calibration you're going to need. And then something we'll return to a little bit later, but what frequency range do we care about? If we have say a fairly sparse set of carrier frequencies, but a wide modulation bandwidth we want to analyze over, we may need a denser frequency list than one might initially thought to cover that. Since if you have large length scales involved in a few hundred megahertz or even gigahertz of mod bandwidth, the point density requirements are going to be larger. What are the instrument requirements? Well, noise floor and linearity are the obvious ones. The path loss comes back into that. What is the transmit power over here, of course? If for test efficiency reasons, we're going to be stimulating all of these elements at once, let's say at different frequencies so it can quickly ratchet through them, how linear is this instrument multiple carriers present? That isn't something that's easily specified. Might need to be characterized separately. And of course, the bandwidth that's required. And along those setup considerations, how are you driving the elements if they are more than one's being driven at once? Are they all being driven at high power? Are they being driven coherently? And the reason that can come up is if there's a lot of coupling between elements, you might get some synthetic load pull going on, which can affect the results as well. That sort of leads us over into our little transition over into the nonlinear measurements. And we talked about the instrument linearity before, that isn't a surprise. But some trends certainly at lower frequency is full waveform acquisition, where particularly for maximum power amplifier efficiency, getting a particular waveform shape is critical. And that hasn't appeared yet at least to my knowledge, in the higher millimeter wave range. If for no other reason, it's really hard to generate that much harmonic power, given the FT of a technology that's being used, say, for a 60 gigahertz amplifier or something like that. But there's certainly, you can see papers starting to show up where that kind of approach is being considered, and that'll eventually be more of interest. Where that comes down to in the measurement hardware point of view is particularly getting at harmonic phase, since being able to measure that is critical to being able to line up a complete waveform. And another fallout from a nonlinear analysis might be, well, should I be measuring all of my network parameters modulated? And the obvious thought is, well, maybe if I need to do it quasi-linearly because of the whole peak to average power kind of concept, which probably everyone's familiar with. But where does one draw the line between network and signal analysis? And probably the answer is it's hard to tell. But let's consider from the network side anyway, where, well, let's create a modulated source. That seems easy enough. If I do have my set of reflectometers talked about before, I can still do some kind of match correction. If I have a reference available, I can do some ratioing, which in the next slide we'll see why that might actually be handy. But then the frequency list mentioned earlier is of course also important again. That, let's say, the carrier frequencies I care about are maybe only spaced by a gigahertz or so, but I've got this pretty wide modulation bandwidth in between. I may need to calibrate on this sublist in between each one. So a dual list kind of frequency approach is sometimes considered. So what about that ratioing and leveling kind of concept? If one was just doing signal analysis, one wouldn't think that'd be important, and it may not be all the time. But suppose in this earlier slide we had some driver preamp, and suppose that's drifting around a little bit. That could impact both the measurement and what the device is doing, and that's really what this slide is showing. If I just treat it as a native single channel kind of measurement and I came back 2 hours later, what actually happened in this case is the drive power drifted up by a couple of dB in band. This is a multi-sign kind of stimulus. But in doing so, that actually pushed the device into a more nonlinear state. So you see the adjacent channel things creeping up. Whereas I have a locally leveled and ratioed kind of signal that could have been counterbalanced by the system, so the drive level stayed consistent and you didn't get that change, in particularly in adjacent channel. It was pretty significant. What kind of measurements can you do with that kind of structure? Well, we could look at gain compression and phase distortion versus drive. That may be of interest. And of course, one can compare to a CW sinusoidal measurement, which is really what's going on here. And not surprisingly, it's a modulated signal, so it appears to be more compressed, even though the average powers are the same, just because the peak powers are not the same. The zones are essentially pulling out portions of the modulation bandwidth and isolating how compression is behaving in each of those. And doing that separation in a full nonlinear modeling sense is something of interest as well. And one can see why, if one looks at the phase distortion versus power, we're actually deviated a fair amount for those two different zones within the modulation bandwidth. Casting that in slightly different terms, just looking at a P1 dB point versus carrier frequency, so the plotting is a little bit different. And of course, if you do it with CW stimulus, the results are, well, different. But what's shown in the lower part of the graph are these zone compression points again, but with and without match correction is really the difference here. So if one compares, let's say, the blue line to the green triangles, the thing of note really is the discrepancy between those two is not constant with frequency. And what that correlated to in this particular case was the match of the DUT wasn't constant with frequency. And another place where that match correction can show up is in the phase through the passband. and that's what's plotted here in the lower picture, where a simple normalization cal showed a fair amount of phase variation in band. So if one just looked at that data in a native sense, one might think, wow, there could be a lot of group delay distortions. There might be higher EVM for that particular part. But in this case, it was more just a measurement defect that would have led to that conclusion. Well, shifting more officially now into signal analysis, what is different architecturally? And historically, there was quite a lot, and certainly lower frequencies there still is, where there's usually more conversion stages to reduce spurious content. You really are looking for an unknown signal, typically. There was pre-selection, some variable filtering up front, again, for spur removal and for linearity assistance and some other reasons. There may have been some of the variable gain we talked about earlier, and that's certainly true. Going towards millimeter wave, there tends to be a bit less of a difference from the network side. The pre-selection typically gets a little bit weaker since the losses through those kind of structures at 70, 80, 100 gigahertz can be substantial. They still exist, but they can be larger. You may have the harmonic conversion we talked about before, so the same kind of issues might creep in with other harmonic products. And certainly the older school millimeter wave harmonic mixers one might have used, there's no pre-selection at all, and there's a whole forest of these of significant amplitude. But then there's some ADC, and that's something we haven't really focused on much yet. But since we already talked about mixers and everything else, let's spend a few minutes about how we digitize data. And this has a lot more relevance now in many ways, just with the availability of high-speed digitizer cards that are used in a number of lab setups, where they have their own block frequency converters to handle the RF side, but just need some good digitizers to process data. So if one looks at linearity of these chains, there could be, I guess, a wide variety of different possibilities. If the front end dominates, which one normally wants from a classical design point of view, one might see a simple curve here. It could get more complicated depending on the mechanisms, but let's just assume it's say some mixer diodes that are limiting. But if instead data D converters dominating, the structure can be a lot more interesting, where at the very high end, you may actually get waveform clipping, so it's an extremely high order nonlinearity. And at the low end, you may get some digitizing kinds of defects that cause a rise that appears to be an intermod product at low power level, which is a little counterintuitive initially. And there are a number of causes for that, but one of them is very classical and just a static integral nonlinearity, as it's called, where there's a little bit of variance of from code to code, just as we can't isolate the level we're at correctly. And if your signal amplitude happens to land in just the wrong place relative to this quasi-periodicity, one gets a little burst in this third order product kind of curve, which is a little bit counterintuitive. And also, if one's classically used to third order product curves having a slope of 3 with power, it actually only happens over a pretty small power range. And you get these other areas of more curious slopes involved there. And particularly when we talked about variable gain up front before, but there's also often variable gain for the A-to-D converter, which is, if you're doing your own digitizers, of course, pretty important to understand. In a normal signal analyzer, the instrument's taking care of that task for you, making sure the level's appropriate to avoid these problems and those problems and things like that. But if you're doing it your own, you have to pay some attention to it. There are cases where this can get confused if, say, spurious energy gets through some of these spur prevention tactics. The A-to-D won't be able to figure it out. It has to figure out amplitude somehow. So there may be some way, sometimes when a manual control is needed, and that's usually available. At the front end, that's oftentimes the user has some responsibility there, even in a full instrument. Particularly if there are wideband interferers coming in that are not in the current measurement range. Another aspect is the clocking itself of the converter. As in many ways, it really is a mixer, and we go back to some of the LO importance issues we discussed earlier. It's not surprising, it will matter when we go into the many hundreds of megahertz or gigahertz sampling realms. And one little example is shown here where we're just doing a two-tone measurement and sampling at 600 megasamples, if I remember correctly. But we have our nominal starting case on the left here, so we see some spurious products running around, which is fine, and noise floor. Our tones aren't equal amplitude. But then there was a mismatch introduced in the clock system. Someone placed a tap into the line without compensating. And at first glance, I might think, well, that actually looks nicer from an aesthetic point of view. But if you look closely, the spur amplitudes really are the same. What actually happened is the noise floor came up. And what happened in this case is the waveform was distorted enough that some samples were missed. And when transformed to the frequency domain, that just showed up as an elevated floor. But supposing we get around those problems, now, okay, we've recovered the signal, now we probably want to demodulate it. And I won't be able to go into any level of detail on this subject. We're staying on the very, very physical layer. But one topic we might have to consider is, well, are we on frequency? And one normally would like to synchronize time bases, but that may not be possible. So there are a number of ways of handling that before one can actually demodulate this funny, curvy-looking modulation zone. One can phase lock on an IF basis, and that's sometimes done either in, well, historically hardware, but more commonly in software now, where the LO is tuned to keep the centroid or some particular aspect of the spectrum where you want it in your IF window. And again, parts per billion accuracy does matter, and that's sometimes difficult to think about. But if you're moving around by, say, 1 hertz, but your data payload is on that same scale, well, you've lost a whole symbol. And a second topic is, even if we have the carrier recovered properly, what about the data itself and the internal clock there? How to recover that kind of information? And there are many ways that's done, but one approach is using a cross correlation, where one knows a particular modulation scheme. One can compute the time alignment to maximize this quantity, and there we have our clock essentially for demodulation. And why I mention it really goes back again to our LO or our clocking to the ADC that we talked about before. If there's an awful lot of jitter on that sampling clock, that's going to impact this cross correlation, how well we can interpolate in particular. And that can lead to some elevated EVM. So again, the importance of the LO control, even if it isn't really an LO. And that brings us to another signal analysis measurement. This one's a little bit simpler. Just say I want to measure adjacent channel leakage ratio, which is a specification in the 5G, 3GPP standard, as in all the previous ones for 4G and so on. But let's look at this in a little detail, as this will bring us back to the uncertainty topic again. But let's suppose we're looking at the widest channel, and this is in the higher frequency ranges, up 28, 38 gigahertz, whatever. But 400 megahertz channel, and the specification is minus 16 dBc, which is essentially the channel power in this little block B relative to that in block A, the in band. And let's suppose our instrument has a max power, or can support a max power of minus 10 dBm with good enough linearity. So that means to meet this specification, the signal from the DUT in the B channel has to be less than about minus 111 dBm per hertz. So we want our instrument noise floor to be considerably lower than that. And at these frequencies, that isn't too hard to do. There are many instruments out there that can accomplish that. So that's encouraging. But what's new compared to some earlier standards is some maximum uncertainties are specified. plus or minus 2 dB in this higher frequency range. And so if we think about that a little bit, if it's really adjacent channel power ratio, that's, I mean, not so bad. We don't really care about absolute power accuracy. So if our power sensors and power cals were invalid, that actually wouldn't hurt this measurement, assuming it wasn't too far off over this frequency span. Repeatability doesn't really matter too much either. I can measure these at the same time. So there'll be some noise and linearity kinds of contributors to uncertainty, and we do have to calibrate for the receiver's slope over this roughly 800 megahertz range. But that seems not too bad. But there's another specification for absolute power in B over, I think it's a subset of this channel width, but there's an absolute power specification. They give an uncertainty allowed there of 3 dB, and this is of late last year. I'm not sure if this number has changed. But this is a lot more challenging measurement if you think about it, in that now, okay, it's absolute power. Now I have to transfer some power sensor accuracy to my receiver. So there are more calibration residuals to worry about. There's some repeatability concerns since I have to, particularly if it's over the air, between calibration time and measure time. There's some mismatch to correct for relative to the power calibration time. So this is a lot more challenging kind of measurement, even though they do allocate a bit more uncertainty. And shifting gears now into time domain, if you notice, the structure doesn't look a whole lot different from the earlier pictures, aside from a little more detail. But of course, in practice, there is a fair amount going on, particularly in the realm of triggering. Now, all the analyzers before have some kind of acquisition triggering kind of scheme that's required, but there's obviously typically a lot more choices in a time domain tool, since you're looking for transient information, generally speaking. And importantly, there are two varieties of that kind of triggering. One is on the acquisition level, and one is when looking at data after the fact. So you might have some very deep memory, many gigabytes of samples, and in looking for patterns in the data, for example, edges on two channels coming up at the same time, what happens next, or you're looking for glitches or other structures. But many of the same topics come into play that we talked about before. Well, how clean are these sampling clocks? That'll affect not only the ability to time resolve items here, since jitter here acts like a low-pass filter, but also distortions introduced in the data from clocking errors. Diving a little deeper into what a real-time oscilloscope might look like. And there are, of course, many ways of doing this as well. But one approach is to have a number of slower speed A to D converters that are multiplexed together, that are slightly offset in time at when their data was held for sampling. So of course, the secret part of this, or the hard part of this, is getting those little taus correct. And there may be calibration routines internally, training signals, or other things to handle that task, temperature compensation, among others. But again, controlling these LOs, so to speak, ends up being one of the performance determining parameters. And interestingly enough, some of the high-speed A to D converter chips one can buy basically have this kind of topology implemented internally. So you don't actually need a whole instrument to get that kind of structure sometimes. And what's also interesting from a block diagram point of view is one sees some test structures where one actually incorporates a block down converter up front to get even larger bandwidths. And these may be switched block converters to cover the whole frequency range. But you get a little even more convergence of some of these measurement structures than we did earlier. So the applications, of course, they're all over the map for time domain tools, and they're so powerful. But one interesting application has been back to our power amplifier kind of question, where people are looking to acquire voltage and current waveforms at microwave and millimeter wave frequencies. Now, this happens to be down in the cellular bands, but you get the idea. And what's pretty interesting from the block diagram point of view is how similar this looks to how we started this talk, where you have some directional devices, you have some source that has to be switched, and you just replaced the heterodyne system with essentially an oscilloscope. But the measurement objectives are the same, and many of the same calibrations of these planes that we talked about come into play. And one can carry that a little bit further in that we can use this structure to look at a modulated millimeter wave waveform. And this is just a very simple modulation, BPSK, on a 220 gig waveform with frames. So what's interesting is the 3 different time epochs that are sort of in place simultaneously. The phase modulation kind of time epoch, the frame envelope time epoch, which is the slowest of all of those, and then the RF epoch, which is now in the a couple of picosecond kind of range. But with this kind of structure, which is sort of harmonizing some of all the block diagrams we talked about, one can recover the modulation information. Carrying that a little bit further even, what if we broaden this to bring in some transient aspects as well? And so let's suppose I had a multi-sign kind of signal that's applied with an envelope on it, some kind of framing envelope to a transmitter. And we're interested in the time evolution of distortion products. We'd like to do some match correction. We'd like to do a little comparison of the input waveform. So what does that sort of mean? Well, time evolution, so that says transient nature. So we're going to need some kind of triggering help. We're going to need some kind of waveform memory. That makes sense. We want to do match correction and some input ratioing. So, okay, we'll probably need multiple receivers, and they are going to have to be linear. And we're looking at distortion products. So the frequency plan of the stimulus and receiver are different. So we're no longer in, certainly not in a small signal S parameter realm. That's quite certain. And so one can imagine an instrument and accomplish these kind of things, which, as you would guess, is bringing together some wideband IF concepts, some deep memory, multiple receivers with some kind of signal generation capability, and some means of incorporating triggering and modulation. And so here's such a measurement. And on the lower part of the screen is really sort of the evolving time epochs that are interested. There's some global start trigger. So we're going to power up this transmitter at some start time here. Bias is going to start, the signal is going to start. And then the frame blocks are going to start propagating to the transmitter. One on the initial one we're going to look at, and then about the 8th one we're going to look at. In the graph, we show one of the main multi-sign outputs. This is sort of the carrier, if you want to think of it that way, or part of the modulation. And that's in green, and so there's a little bit of overshoot at the start of the frame. That's interesting. And the blue is just the noise floor of the instrument, so that's less interesting. But if you look at the dashed curves, those are the intermodulation products. And the red one's measured in this first frame. And you see, okay, it peaks up near where the main tone has an overshoot, so that one could rationalize why that should happen. And there's a little bit of evolution over the scale of 10 nanoseconds or 15 nanoseconds or so. But one looks at the purple line, which is what's going on in this 8th frame. One again sees this peak up near the overshoot point. That sort of makes sense, but the amplitude is quite a bit lower. And what ended up happening in this particular system was a driver amplifier warmed up as it went through these first 8 frames. Its gain dropped a little bit, so the final stage was compressed a little bit less and hence a little lower in terms of distortion. But it was by combining a lot of these architectural thoughts in this measurement, we were able to accomplish this kind of measurement that brought both time and frequency aspects, distortion and match correction and the other network and signal analysis concepts together into it. So to summarize, there certainly as we're moving into these higher frequency realms, there are changing power budgets. Linearity presents some interesting cases, may not affect uncertainty directly, but one has to think about it more and more. Calibration needs are changing more with media than anything else, but that's being driven by the integration requirements of those applications. And across the instrument types, there are, I guess, a few recurring themes. One being the increasing importance of clock and LO, purity and stability, and how one modulates that waveform. Wideband digitizers are ubiquitous in all the instruments, and of course as a standalone kind of tool. And understanding their linearity, sometimes the other vendors do it for you, but taking that into account may sometimes be needed. The centrality of repeatability and drift as an uncertainty mechanism, and understanding how things like mechanical mounting schemes interact with this, as well as even mechanics of connection schemes. And it's sort of tangential in a little bit, but the importance of how data is used in the end and how some of these uncertainty mechanisms propagate through it. It may be some of the transform related items we talked about, which are increasingly important, where correlation comes into play. It may be simpler, such as a nonlinear transform. For example, a device modeler may want to express everything in Y parameters for their purposes, but that's a nonlinear relationship from the S parameter space, and the uncertainties propagate a little bit differently. And all of those impact the acquisition needs and how the measurements are set up. But with that, I would like to thank you very much for your attention, and happy to entertain any questions.
Hey, John, thank you for a great presentation. We do have a couple of questions here. Let me just quickly bring up this first one. How does frequency, phase, LO mismatch manifest in data recovery?
As in demodulation, I assume that's referring to?
Yeah, we'll leave that's what it's referring to.
Yeah, that's actually an interesting one. There are a whole lot of places that shows up. If there are phase distortions that say impact the modulation envelope itself, then the data curve that comes out will be misshapen. So identifying a symbol edge gets to be more difficult. You may miss the edge entirely. You may sample partway up a symbol transition when you shouldn't be. So that leads to, well, EVM spreading if one looks at a constellation diagram. If you have linearity issues, that can certainly compress a symbol, particularly for some of the multi-level kind of signaling schemes. That gets to be even more severe. So the whole constellation can compress or expand. And certain phase distortions and depending on the detection scheme, other bias distortions can rotate that whole spectrum. And what that all boils back down to identifying the symbol edge correctly, so you sample in the right part of the symbol.
Great, and then so one other question here. Can you comment on generating nonlinear models for system simulation?
Oh, that's a big topic.
Well, if you can just yeah, maybe lead someone to the appropriate area to research.
Yeah, there have been a number of DML talks in recent years, actually, on the nonlinear generation. Professors Roblin, Schurz, and Pedro among them. They're Jan Verspect, whose paper I cited earlier, are good places to start. There are a lot of different philosophies there. One is based on the premise that there is a core to a model that's largely DC based, and the DC behavior determines all the nonlinearities. And then there are RF parasitics that surround it, and those, from a use point of view, sort of determine the nonlinear behavior you see in practice. So in that school of thought, they focus on heavy low frequency and DC characterization to capture memory effects, capture all the IV distortions and everything else. And then they carefully try to go after all the RF parasitics separately and create a separable model that way. Another school of thought is a full black box kind of approach, where you characterize this whole RF microwave blob as something that responds to different stimuli in the RF and DC space. And in that case, one would do a stimulus map over different, say, RF drive amplitudes simultaneously with different bias conditions, and fill in as much of that surface space as you can. And there's a large body of literature on that kind of topic on how to efficiently cover that n-dimensional space and get a predictable model over both local ranges, say if you're only going to move a little bit around a specific operating point, or much larger ranges where one wants to predict how the device can act in a number of different applications. So there are probably other schools of thought. Those are the two I'm most familiar with, but they can both yield pretty good results.
We've got a couple of other questions here as well. With the advent of wideband digitizers, do you see the blending of separate measurement devices like VNAs and oscilloscopes?
That wouldn't be surprising if there's more of a convergence. Because we've already seen in, say, how the various instruments act today as opposed to a decade or so ago. You see oscilloscopes that are doing open short load calibrations with couplers, and you see VNAs with deep memory for capturing transients. Yeah, so it wouldn't be surprising if there was a pretty significant degree of convergence.
Okay, and I think we may just have enough time for one more question. This is, how does the digitizer noise performance affect the performance? Is it a function of bandwidth?
Of course, if you're looking on a trying to acquire the entire available digitizing bandwidth for whatever reason, its noise floor is going to be higher than if you're after less of it by a Fourier means or some other approach. Now, on an equivalent bandwidth point of view, typically a faster digitizer is going to have a higher floor than a slower digitizer, just for certain technology reasons and how they handle the sampling clocks. That discrepancy is decreasing over time as the technologies get better and the internal calibrations get better. But there probably will be a little bit of a noise floor hit on a per unit bandwidth basis if you sample too much faster than you need to.
Okay, great. We have one other question here, more relating to logistics and the availability of the slides or recording. And gosh, maybe you can comment on that, whether how people get access to that.
Yeah, so as mentioned before, this talk was recorded, and the link to the video as well as the slide set will be sent to all the registrants, so everybody here will get it.
Great. With that, I'd like to again thank you, Dr. Jon Martens, for a great presentation. I think it had a lot of people tied up in your presentation. So again, thank you, and I think I'd like to close the presentation at this point. Thank you very much. Thank you very much for all the attendees and their participation.
Thank you, everybody, and stay tuned because we'll be back next month with our next talk. And yeah, hope to see you all there. And thanks again to Dr. Jon Martens. This was a very good talk, very informative. So thank you.
Thanks, John.
All right. See you next time. Bye.
Right. Bye.